Imagine if you could hit the pause button on something happening at lightning speeds, like freezing a burst of energy mid-air. That's exactly what a team of physicists just achieved with silicon, a material critical to electronics and solar cells. Here's how they pulled it off, and why this breakthrough could redefine material science. The problem: melting faster than we can blink. Silicon, when blasted with an intense laser pulse, melts in a mind-bending 0.1 trillionths of a second. This non-thermal melting happens so quickly that atoms lose their structure before they even heat up. Scientists at the University of California, Merced, in collaboration with German researchers, wanted to bottleneck this chaotic process. But here's where it gets controversial. Their solution involved more energy, not less. Splitting the pulse to pause the chaos. Meet the team's clever hack: slicing the laser energy into two precisely timed pulses. The first pulse, like snapping a rubber band, sets the atoms in motion. The second arrives just 126 femtoseconds later. That's 0.00000000126 seconds. Acting as an atomic traffic comp, it freezes the motion, creating a temporary state where the material remains solid despite absorbing the energy that normally causes meltdown. This is no technical glitch. It's the science of metastable materials, a kind of temporary crystal. Why this matters beyond silicon? But wait, there's more. This pause state retains key electronic properties like reduced band gap, a trait coveted in semiconductor tech. Even more surprising, the atomic vibrations, phonons, stayed miraculously stable, as if the material had cooled down during the pulse sequence. Researchers used advanced computer simulations, ab initio molecular dynamics, to map this atomic dance. Modeling interactions from first principles, no approximations here. The controversy: should we harness chaos? Here's the rub: should science always aim to control and stabilize, or might rapid material changes, like intentional melting, unlock new technologies? This approach could enable new phases of matter, or it might overshadow the study of natural energy transfer processes. The team suggests their method could apply to other materials disposed to ultrafast phase changes. But what ethical and practical boundaries does this open? Future directions: bending light and matter. The study opens doors to refine experiments measuring electron-atom energy transfer, crucial for fields like fusion research and nanotechnology. But big questions remain. How precise can we get with pulse timing? How scalable is this for industrial applications? And what's the environmental impact of scaling these laser systems? The takeaway: science as a game changer. In plain terms, this is border-pushing tech. By tricking silicon into a temporary solid state, these scientists aren't just solving a material problem, they're rewriting the rules of energy-material interactions. Whether you see this as groundbreaking innovation or a risky manipulation of fundamental physics, one thing's clear: the interplay between light, energy, and matter just got a whole lot more nuanced. Citation: Tobias Zier et al. Pausing ultrafast melting by timed multiple femtosecond laser pulses. Communications Physics 2025, DOI 10.1038/S42005/02383, http dxdoi.10.1038/S42005/02383. Your turn. Should science prioritize controlling chaotic processes or studying them in their natural states? Could this approach backfire, causing unintended material instabilities? Share your thoughts below.